So as mentioned this morning during Jay Metz's presentation, Craig Carlson was not feeling well. He was going to give a presentation in this session on AI, but he is obviously not available. So instead we've got Andy Banta from Magnition and he's going to talk about optimizing multi-tier storage from CXL to cloud.
Good afternoon. As it says up here, I am not Craig Carlson, and I am not playing Craig Carlson. As Jay Metz was earlier today, Craig and I did not collaborate on his session that was supposed to be here. My name is Andy Banta. I've been doing storage development for about 30 years now at a variety of different places, Sun, VMware, SolidFire, and NetApp, and I'm currently the storage janitor at Magnition IO. So everybody has seen this pyramid. I didn't even bother to update the labels on it because the pyramid has been around for years, and the whole idea is the same. We end up with expensive high-speed memory and storage at the top of the pyramid, and lower costs, lower speed storage at the bottom of the pyramid. And you could probably replace 3D Crosspoint with CXL in this case, and probably make a couple of label changes. But the pyramid hasn't changed, and I didn't figure there was any need in attempting to update it simply to show the pyramid. The problems that you end up with it really haven't changed either. They're listed here on the right side of the slide. As you get more layers, the complexity associated with these tends to go up though, and trying to figure out how to appropriately build and size the layers becomes increasingly difficult. We've taken the approach of building a large-scale simulation to allow you to build out the various different pieces and try out these various different tiers to figure out how to best size them, put them together, what components to use. And the way we do this is we've built a framework where you can build various different components and put them into the simulation, arrange them in various different ways, connect them the ways that you want to, size them the ways that are appropriate, provide some way of giving some variables and some constraints to it to allow it to be able to change. So this could be changes in size, changes in construction, changes in the way things are connected together. And then the framework will allow you to run simulations against these. And you can use synthetic data, but we also have harnesses to allow you to use actual traces. So you can use HTTP traces, you can use IO traces from like a network trace or a vSCSI trace on VMware. You can also use memory traces. You can do this by actually simulating CXL and then capturing the PCI traffic and using that as the basis for your simulation. So there's a lot of different things to understand about tiering models. In this case, let's take a look at the some latencies with various different cache sizes. And here you can see that with a little bit of cache, we get some improvement, but then we can keep increasing the size of the cache by 2x, 4x, 8x, and we really haven't improved any more performance that way. So you could end up spending lots of money building out your cache without seeing any real improvement on it. And while it's easy to see this while you look at this graph, keep in mind that you can't see this graph when you're running the experiments on it. You can't actually know what it is unless you run all of the experiments and figure it out ahead of time. If you're going out and just keep cramming cache into a server to try to figure out where the best point is, you're going to be doing a lot more experimenting, and you're going to be spending a lot more money and time to do it, as opposed to doing it with a simulation. As I said, this is an invisible graph until you actually do the experiments to figure it out. And we can have this applied to multiple tiers as well. What the first one just showed, a single tier. In this case, higher is better because this is throughput, workload throughput, not latency. But you can see that as we add various different tiers, the workload accesses farther and farther tiers of memory and storage, the throughput goes down. So you can actually see this type of information about running your workload as well. Has a bunch of different use cases. So what I've just shown you would be like a monitoring work case where you actually just want to figure out what's going on in your system. But you can also use it to select policies. So the discussion that Curtis gave this morning, talking about AI having various different use cases for storage during various different phases of the AI, you could actually have your storage be auto-adapting to that phase to make best use of the way to cache things appropriately for that phase. And if you're somebody who's actually providing cloud services in an enterprise, or if you're a cloud service provider, it could be that you actually have latency guarantees for your customers. And this was one way of being able to observe and make sure that you get your latency guarantees in. And you can actually figure out how to appropriately size and place the tiers of your storage by just doing these simulations rather than building out your entire environment. And the fallout of some of this is that you can figure out ways of reducing your latency. So you can go through and do a handful of experiments to figure out where the best way to get rid of your latency is. And this comes in really handy when you have multiple tenants and you're trying to figure out how to make best use of their resources and or how to make best use of the resources you have for those workloads. And so you end up with a handful of results being able to run these simulations. You can figure out the changes, you can figure out cache efficiency, the various different options or various different results that I show there. So let's show how this works. One of the experiments that we put together is a fairly simple one. We just, with CXL, we're ending up with situations where a single processor can end up with 7 different NUMA nodes, or numerous different NUMA nodes. In this case, we have 7. Each one of them would potentially have different latencies. So the whole idea here is that the distance from the CPU is higher and the latency for that memory ends up being different. So the experiment the reason we put this experiment together is wouldn't it be nice if you could actually test drive CXL? Because another thing with CXL is you actually can't buy a lot of components yet. They just aren't on the market. There's no way that you can go out and try them. But if you can simulate them, if you can do a behavioral simulation of them, you can do a test drive of them. So here's the first experiment we did, and this is what we just considered a baseline, where we have a handful of different applications. These are synthetic applications in this case, but they all have about the same memory footprint, and we have a memory system, and this has some locally attached DDR, and then we'll also talk to a swap drive. In this case, the applications run in different ways, but they all have about the same working set, so they all have about the same amount of memory they need. And in this case, we sized it so the applications would fit in the amount of local memory we have. So we tried starting them in various different orders, and we end up with very similar results here. In the case of just running one application, it takes a certain amount of time, but the memory latency is immeasurably low compared to running 2 or 3 applications where you need to start swapping. So the second experiment we ran, there's still swap connected to the system, but we connected what would be considered local CXL, which would be CXL that is inside the server box, and far CXL, which would be CXL which would be connected through a switch. And again, these are simulated. We chose arbitrary latency and latency spreads for each one of these to come up with what we considered, a realistic experiment. And we tried running the various different applications, but we just tried starting them at random times as opposed to each other, random delays between them. And here are the results that we get. Now the latencies are measurable. If we go back, we can see that our latencies were in the 350 millisecond range or 35,000 millisecond range. And here we're talking about it, I think that's actually microseconds. I guess it says nanoseconds. In this case, you can see our latency is back down to a normal amount. a reasonable amount for memory. But what you do see is as we start each application, the amount of runtime it takes for the applications to run to completion goes up, and the amount of latency the various different application use changes as well. And you can see in the first and second application, the amount of latency they have goes up when you start running the third application as well. In VMware and Linux, you have the capability of actually telling each application, use this NUMA node. So rather than just going out and allocating memory as it's available, you can actually pin processes or pin virtual machines to various NUMA nodes, and that way you end up with consistent runs for those applications. This type of thing would drive performance engineers nuts. Performance engineers hate this type of indeterminism when your applications are running. So that's exactly what we did, and we ran the various different applications, each with their own NUMA node, and we can see that in each one of these cases, whether we run 1, 2, or 3 applications, the entire runtime is exactly the same, and the latency of the applications, of the memory latency of the applications doesn't change either. So and I apologize, the numbers here are incredibly small, but the total runtime came down for it as well. So in this case, the total runtime for all 3 applications is less than it was in the first case, where here we're running almost 90 seconds to completion, and on this side we're running 50 seconds to completion. So this is one of the ways that I was showing you where we end up with latency consistency. This was one of the use cases I showed you before this as an example of something you can do. And putting this entire experiment together and running the several hundred examples we did on this took a 1 week of engineer time. So this was using the framework that we put together. We built out this model and ran the several hundred experiments in 1 week of engineer time. So yes, I'm sorry.
Were you ever able to establish the veracity of that in actual hardware?
No, we do not have a hardware budget to buy CXL equipment. This was simply an example. This was a talk that I gave at SDC with Craig Carlson, ironically enough, about CXL and the ability to test drive CXL without actually having it in your lab.
Quick question.
Yes.
So, in your studies, was there any indication of the number of NUMA nodes? Did you guys get to do any studies on the NUMA nodes?
We certainly could. I'm sorry. The question was, did we do any experiments where we varied the number of NUMA nodes or changed the various different numbers of NUMA nodes? And in this case, no. We were aiming at a very specific experiment, which was getting performance consistency, and we pretty much knew the model that we wanted to go after. You certainly could, and it certainly wouldn't take that much more work in this framework to build out that type of simulation. So something that was a larger scale effort was doing the same type of experiment on content delivery networks. And I realize that we're storage folks, so not everybody might know what a content delivery network is. Things like YouTube or your newspapers or photo stores or various different other things are essentially content delivery networks, or Amazon Prime for streaming services. These are networks that are intended to deliver content to your personal device. And they don't just have a big server that's sitting somewhere where they pull everything off of when you say, I want to watch this movie or I want to see this video. They have various global points of presence all over the world, and these points of presence are hopefully closer to you than their main server, and hopefully have the content that you're interested in cached. So if you want an example of something that would not be cached, go look up an SDC video from 2022, and you will see that YouTube takes 20 to 30 seconds to bring up that content for you because it's not cached in a POP that's local to you. But this is the general idea of what a content delivery network is. And if we take a look inside the various different POPs. There are typically a handful of servers, and most content delivery networks do use the two-tier caching system that I have shown here, where they have some DRAM cache and they have some SSD cache. And in these cases, if you don't hit the cache in the local POP, it has to go to the content provider origin. In that case, go back to YouTube Central to find that SDC video from 2022. So there's a bunch of different experiments that we tried here. You can do things like try having some of the servers that don't have any DRAM cache have SSD cache only. We did the opposite, where you had DRAM only and no SSD cache. We had setups where each server had its own independent SSD cache, where they had no collaboration between the various different servers. We also did experiments where there was a shared SSD cache across all of the various different servers. We played around with the load balancer in this case to figure out how to appropriately direct the request to the appropriate server to serve it. We did things like, in a typical, when you think of storage, you think of your caching happening from fastest to slowest levels of cache. So in this case, you would cache something in DRAM first, and then potentially push it down into SSD. With content delivery, you might want to take the different approach of where you actually put it in SSD first, at first request, and then later on, if it gets more hits, you promote it to DRAM. Because in this case, you probably are going to cache it at first hit because it's gone off and it's had to pull it from the content origin already. So let's store it. And there might be more hits coming, and if that happens, we'll promote it to DRAM because that'll be a faster way of serving it. But if it only gets hit once, you don't want to be wasting your DRAM by storing it there. And we looked at, one of the other things that we had a lot of fun with was looking at various different eviction algorithms for both DRAM and SSD cache, and using disparate eviction algorithms. And this is really important because you actually want your content to be cached on one of these POPs rather than having to evict it unnecessarily and then having to go back to the content or provider origin to get it. So with the CXL experiment, we ran on a bunch of synthetic data. On this, we ran about 900,000 experiments, and we ran them against a couple different data sets that we were able to get. So we were able to get HTTP traces from Wikimedia and from Cloudflare. And we ran about 300,000 experiments against the Wikimedia HTTP traces and about 600,000 experiments against the Cloudflare experiment traces. In this case, you can see that the red dot is the baseline. So the red dot is the performance that you would have gotten if you were using the Wikimedia or Cloudflare traces and you were using their configuration, their setup to do it. If you were using the way that they had set up their caches. And you can see that Wikimedia, being a public nonprofit organization, hasn't done that much work on optimizing their setups. And you can see that in our various different 300,000 configurations, we outperform them most of the time. You can see that Cloudflare actually spent a lot more effort in optimizing it because Cloudflare is a commercial for-pay content delivery network. And in fact, you can see that their baseline is better than the median for all of our different 600,000 configurations. The line in the center would be the median configuration. So Cloudflare has actually done a fair amount of optimization. But you can also see that we came up with some configurations that were better for those particular traces that we got from Cloudflare than what their baseline was doing. And we shared this information with Cloudflare if they're interested in doing any of the optimizations that we've done. And the cool thing about this is that you don't have to just optimize for one variable here. So we decided, let's try to optimize for byte miss ratio, essentially how often you're trying to hit something in the cache and you miss. And also, let's let's try to optimize for cost. So we took these various different data sets and tried it out, and for minimum byte miss ratio, you can see that with Wikimedia, we're way below the baseline, the dashed blue line of what they were getting for our minimum byte miss ratio, and at a slightly higher cost than they had. You can see for Cloudflare, this experiment shows much the same thing, and again at a higher cost. If we minimize it for cost, you can see that in both cases, the byte miss ratio is not as good as the baseline for either one of these. And then this was done by a grad student, and she was trying to come up with what would be an ideal use case, and that was what's labeled the research case here. And you can see in the research case, the cost came down a little bit for Wikimedia, and we only had a little bit worse byte miss ratio, but we're still way below the baseline of what they had. And you can see in the Cloudflare case, with the research case, we almost had the exact same byte miss ratio that they did, but we came in way lower in cost. We were about half the baseline, the red dashed line for baseline cost. So we were able to show a handful of different things. And again, we would provide this we will provide this information back to Cloudflare if they say they're interested in it. We do talk to them. You cannot just go to Cloudflare and ask for their HTTP traces. This was a proprietary exercise we did with them. But the other thing I want to show you is that we ran, as I said, about 600,000 different experiments, and we ended up with all sorts of interesting plots on various different comparisons that you can go look at and go, try to figure out what works for optimizing things and what doesn't. And on some of these, if you actually need to kind of draw in the lines to see what the interesting data is, but you can see the interesting basically cliffs and horizons that you end up with, where you can say like in this, in like the far square third from the bottom, you can see that in whatever the variables were, the first two made most of the improvement, and then it leveled off. So this is the type of thing that you can spot very quickly by having all of this data available to you and having it something that can be graphed rapidly. And so the whole point of this is that these simulations can be used for a variety of different tiering work. It's not just, it's not a single use simulation. This framework can fit just about anything in technology that has more than one tier. It can be used for a variety of workloads. We showed a memory workload, we're showing a network workload. It works for storage workloads as well. And it's a way of finding out a multi-objective, or solving a multi-objective problem with less time, less money, and less effort than actually building out the entire configuration and doing it on your own. And this was all done by Magnition. Magnition.io is a very small company. Most of Magnition's public work right now has been research papers and information about various different cache levels. We do have some very successful use cases from vendors that won't allow us to talk about them, but we have had some commercial success. Feel free to contact me. You can contact any one of us at magnition.io, and I in particular am Andy.Banta at magnition.io.